Je schlechter der Fett jetzt.
Er hat auch Dauerkarte.
Ja? Also links, also von der. Ja. Geil. Ja, weil ich würde, ja. Draußen auch wieder lassen.
Das dauert von unten, aber Bock mehr jetzt. Reiseakte schiebe.
Okay, ich lass lieber hoch.
Let me try to summarize where we are, right? I mean, we actually already did a lot last week. So what I introduced you to last week was what I call the neoclassical model, right? I spent some time explaining why I think this model is important, right? Just make it very clear. This is not a model of the real world, right? This is a model, and this is a model which is really a tool for teaching many things that we believe in macro are important, right? And based on this model, you can actually make all kinds of things if you know the tools that I will show you based on this model, right? So that was basically my motivation, right? And I mean, we've really already done a lot last week, right? So I showed you last week in the neoclassical growth model how the firm problem looks like, how the household problem looks like, how we solve these two, right? So that's the typical of the right on first order conditions, right? We describe the optimal behavior of firms and households. We define market clearing conditions, and we actually also define the general equilibrium, right? So these first three steps here, this is what defines your model, right? This is what defines your economy, your environment here, right? And then we actually made a first step, and this is where we got stuck last week, and this is where I want to continue today, is with what I want to call model analysis now, right? So this first part is define your environment, define where you are, right? Think about how agents behave. And now the second step is, now let's use the model, right? So now we want to find a way, first of all, to actually, in a way, already solve the model. We do that in a more explicit way later, but we kind of also do this here now, right? And think about what the model actually implies. What does it teach us, right? What can we learn from the model, right? This is where we are now, right? The first step was defining the model, right? This is now using the model, right? So that's basically where we are, right? And I mean, as I said, this is a lot about teaching you tools, right? And the main tool that I teach you in this model analysis section is this phase diagram, right? That's what I wanted to show you, right? So basically where we got stuck last week was basically this figure here, right? This is where we're going to go now, right? So this is a phase diagram that describes the dynamics. So if you want the solution of the neoclassical growth model, right? This is just a figure, right? But I will hopefully get across how to interpret this, and I will also show you what you can then do with this figure, right? Because we can actually use this figure to then do model analysis, right? In the sense that you can change some things here, some parameters. We actually, on some later slide, I actually have an application where we will introduce fiscal policy in this model, right? And see what it does, right? So that's basically what you have a model for, right? So far we were using definitions or assumptions, or however you want to call this, right? We were defining our model. Now let's use the model, right? And the tool I want to show you how we can use the model is this phase diagram. Right? So this is like a first step, right? So in this chapter 4, I show you this phase diagram, which is more like a qualitative way of looking at the model, of solving the model, understanding the dynamics of the model. In a later chapter, I will show you the full quantitative way to do this, and we will actually have computers solve the model at some point, right? Here this is a bit more like by hand, maybe the old style way, right? But I kind of like to show you this first, because to me computer to solve this. This is something you can always do later, right? And I mean, this is basically what you do later, right? This is also what I do in my everyday life, right? So I'm not saying this is what we do, right? You will have to find papers that still do this because on computers you can do all of this. But this really helps to understand what your computer does, right? So this is why I have this, right? Okay. Yeah, this was basically this here, right? So this is the definition of the phase diagram, right? So what the phase diagram is doing, and this is why I think it's nice, right? It's a way to look at the dynamic problem, right? This is the underlying thing here, right? So we are facing a dynamic model now, a dynamic problem. So we have a t involved, right? Time plays a role now, right? So this is why with xt's floating around, or in our case kt's, right? So like basically today matters for tomorrow and the other way around, right? Roughly speaking, right? And the big advantage of a phase diagram is it's basically a way, even though it's like just this two-dimensional figure, right? To think about dynamics graphically, right? And this is what makes it useful. Okay, so what I already showed you last week was basically the first part of the phase diagram. So what I focused on was basically to say, okay, strip down the neoclassical growth model, and I mean, this is basically something that you will always do with any macro model, right? Because I mean, the problem basically is always these macro models become big, right? Because at some point you start thinking, yeah, maybe banks play a role, maybe unemployment plays a role, so you start making your models bigger and bigger, right? But to actually like strip it down again to solve it, you always need to bring it really to the core, right? And this is kind of what I do here with the neoclassical growth model. And you can really, like, all these equations that I showed you before, you can basically summarize this all in just these two equations. And that's one of the advantages of the neoclassical growth model. In the neoclassical growth model, you can basically summarize everything in terms of the capital stock. So it's all just about K, right? KT plus 1 and KT, right? Which is basically determining everything. And this is basically what I said here. So it's these two equations. Right? So what are these two equations? What's equation 40? Okay, I should go from here to you. That's the Euler equation, right? I mean, that's what I was already talking about in chapter 3, right? So basically describing the demand side of the model, the household side, if you want to, right? I mean, for example, like one thing we're already using here is that the real interest rate is equal to the marginal product of capital, right? Which comes from the firm side. But except for that, this is the Euler equation, right? This is this law of motion for capital, basically using our resource constraint. Right, this is equation 15. And we already talked about equation 14 last week. Right? Basically, how I started was to say, okay, with a dynamic model, it's always good to think about whether there's something like a fixed point you can refer to. This is what we call a macro steady state, right? So let's think about whether there is a steady state, right? And this is exactly what we did here. Right? So what is a steady state? A steady state implies that your variables do not move over time anymore, but they are constant. Right? So in this case here, the Euler equation, consumption would be constant over time. Right? Which means CT would be equal to CT plus 1 would be equal to C, and this would hold for any CT. Right? It would also hold for CT plus 100 or CT plus 1000, right? Constant means constant, right? Across every period, right? And this is what I said in my notation, the following: whenever you do not have an index, right, on this variable C in this case, or here also in K, this implies in my notation that this is a steady state variable. Okay. So this defines the steady state, right? And what happens if you impose a steady state condition, right? So you say you impose in your model, I'm looking for a steady state. What happens if I'm in steady state? What happens to the Euler equation? good story is with the other equation, it becomes actually much more simpler, right? So this was my equation 16 here, right? Because if you impose that C is constant, this left-hand side, it just cancels, right? If CT plus 1 is equal to CT, these two terms here are equal to, and then this is just equal to 1, right? And then you get this equation here, and this is actually, also from the perspective of the phase diagram, a very simple equation, right? It's just one equation in K, right? This depends on the capital stock. It basically tells you that this consumption equation, this Euler equation, right, determines any given level of consumption for one particular capital stock, right? And how does that look like graphically? And that's what I showed you last week. This is this vertical line, right? This is the capital stock, which belongs exactly to this F prime K, right? So the capital stock in steady state. And basically the Euler equation will make sure that we're basically matching any level of consumption. Right? So that was this vertical line. And we also already discussed what happens if we are to the left and to the right, right? I mean, I'm basically like how I started this to say, let's look for a steady state, right? But I'm not saying that we are always in steady state in this model. We're far from that, right? We will be out of steady state many times, right? So let's say we are in a situation here, right? We are to the left of the steady state capital stock. So we have an economy where the capital stock is lower than the steady state capital stock. What would happen according to the other equation? So if the capital stock is here, yeah, go ahead.
We will accumulate capital in each period.
Exactly. Why do you do this? If the capital stock is lower than the steady state capital, what does that mean for the marginal product of capital?
It's relatively high.
It's relatively high. This is exactly why this is happening, right? So like saving, investing in capital is very good, right? The marginal product of capital is pretty high, so let's do this, right? Let's invest more in capital, right? Your households and your economy will do this, right? So you save more and invest more, right? So this first of all brings you some point closer here, right? But what does that mean for consumption over time?
If we save capital and grows, then overall we also have more consumption.
Exactly, right? At some point in time, so not today, right? But in the future, with more capital, we have higher income, we'll have higher consumption, right? So this is why that was the figure that I gave you last week, right? Where I basically said, okay, let's think about how we plot this in a KT-CT diagram, right? Where this here would be in a phase diagram. This is this vertical line, right? And we said whenever we're to the left, C will over time increase. And that's basically exactly what you have here, right? This is this here. Whenever you're to the right, you have exactly the opposite, right? Whenever you're to the right, so your capital stock is higher compared to the steady state. The marginal product of investing in capital is lower, and people will not do this as much, so the consumption over time will decrease, right? So if you're to the right, C will fall, right? And this is kind of what I mean here by, even though this is just two-dimensional, right? You have no T on the axis, right? This here tells you how consumption behaves over time, right? And in my other figure, I mean, this is basically what I'm plotting here is also here, right? So the way to read this figure, this is actually these arrows, right? So this is this vertical line that gives you the steady state of the Euler equation, right? And what you can see here is that whenever you to the left here consumption goes up. to read this figure is basically these arrows that go to the top and that go down. They correspond to this axis here, right, to the y-axis, where you have C on that axis. The arrows that will look left and right, those will correspond to the capital stock. We haven't talked about that yet, right? That's coming next. Right? But this is basically the way to read this figure, right? So whenever you're to the left, this figure tells you consumption is going up over time. Whenever you're to the right of this vertical line, consumption is going down. Okay. And this is where we start, right? Questions? All right. So I mean, as I said, we're not yet done, right? This was basically equation 1. This was line 1. We are missing this second line here, right? So the question is, where does that come from? So I should not put too much into this figure because I will have to put more into that figure and then you will not be able to see anything anymore. Alright, so yeah, so that was the other equation, right? This was the first equation, right? There's the second one, right? What's the second equation, which is like crucial for the neoclassical growth model? This is what was this equation 15 before. This law of motion for the capital stock, right? I mean, just to remind you, this equation is telling you nothing else. It's the future capital stock, it's yesterday's capital stock, minus depreciation, plus your production, minus what you consume, production minus consumption, this is investment, right? So this is really just basically what we would call an aggregate resource constraint. It's basically falling out of bookkeeping, right? This equation, right? This is not at all about behavior or anything, right? Behavior in micro foundations, this is all in here, right? This thing here is in that sense super boring. And it's, by the way, this equation is exactly the same as in the solar model, right? This is not at all different. This is also where I said understanding the solar really helps, right? I mean, what is different is this guy here. This here is just exactly the same as you have in any solar model. So this is also why what's coming now may look familiar to you, because it's exactly what you do in the solar model, right? So again, let's consider whether there is a steady state, right? So let's say we impose there's a steady state of capital, right? So the capital stock stays constant over time. So instead of having all these KTs, KT and KT plus 1, we just put in this little K, right? Steady state K. So again, I mean, this makes this equation, it looks much nicer because then you can basically cancel these two K's here, right? You have a K here and a K here, and you get the K minus delta here, which I put here on the right-hand side, joined with the F of K, right? Again, also steady state now, right? And then minus CT, I put that on the left-hand side, and you have the CT here, right? So you get this equation here, this equation 17 as the steady state condition. What's the interpretation of this equation 17?
So the production function has an output, and this is equal to what is depreciated every period. So what you produce is equally depreciated at the same time, so you don't have any more growth.
Exactly, you don't have growth in capital anymore. This is the idea of the capital stock. Your argument is correct, but part of what was consumption, right? You're still eating part of what you're producing, right? It's not like you're producing is exactly what you're like replacing, but it's what you're producing minus what you're consuming, right? But that's exactly this, right? So basically, like how it's written here, I would say you produce, right? Output, your goods, right? Part of that has to be used for the replacement of the capital stock, right? That was depreciated. And the remainder you can eat. That's the consumption. Right? And this then means in steady state, right, that you actually, as you just said, then you are in a steady state, right? Because you're just like every period, you're like creating new capital, just exactly the same amount as the capital stock that was depreciated, right? And that keeps your capital stock constant. Right? And this is exactly the same interpretation as you have in the school model. Right? So I kind of hope this equation is right? I mean, another way to look at this is to say, well, what happens if you're, I don't know, if this is not equal, right? Then you could say, if you have a situation where CT is a larger compared to F, okay, probably put a T now because then it's not steady state, right? What happens if this is the condition? If consumption is actually larger compared to production minus depreciation. What happens to the capital stock? It decreases, right? Because then you're eating more, right, than you should have, because actually the depreciation rate of your capital stock was larger. And that means your capital stock is slowly decreasing over time, right? And this again gives you that basically these dynamics, right? This is exactly where I want to go, right? So whenever this here holds, your capital stock will fall, and obviously you can also do it the other way around, right? If your consumption would be smaller, then this, what would happen to the capital stock? Over time. Exactly, and it goes up, right? So I mean, I kind of hope you see this parallel argument, right? Here we were talking about how consumption behaves over time, right? Now we're talking about how the capital stock behaves over time, right? And this will exactly give me these missing arrows that I just talked about, right? So here you can see this, right? Whenever, I mean, actually you do it, right? This will be this equation, right? This condition 17, right? We talk about why it looks that way in a second, right? As you can see, whenever we are below, right, we have exactly the situation. We're consuming less than we could in a way, right? Keep the capital stock constant, the capital stock rises. So this would be these arrows to the right, right? This is this guy and this guy, right? This is whenever we are below this line. And whenever we are above, we're eating more, and we should, to keep the capital stock constant, right? And this is what implies that the capital stock would decrease over time, right? And this is, again, notice this is kind of the idea of how we present the space diagram here. This is now these arrows which are parallel to the x-axis. On the x-axis you have the capital stock, right? So this is where these arrows here tell us something about the capital stock over time. Okay, so this is what the phase diagram is. So why this condition here? I mean, you have it here, right? Why does it have this particular shape? Right? And I mean, for that, you can basically make a very nice argument. And this is kind of what you have here on this on these last bullet points, right? How do I think about how this looks like? Well, maybe think about the derivative of this thing here, right? So if you do the derivative of this condition, right, CT, how does CT change in the capital stock, right? I mean, the derivative of that guy would just be it's just equal to F prime K minus delta, right? And then you can think about under what conditions is this positive, zero, or negative, right? And this then tells you something about how this thing looks like in a KC diagram, right? And it has very clear implications here, right? I mean, this thing here will be zero just under exactly one condition if these two guys are equal, right? So if you put this equal to zero, what falls out immediately is that the marginal product of capital has to equal the depreciation rate, right? Only then will we have that this guy here is equal to zero, right? And this is then this point here in my figure, right? So there's like a maximum, right? This is what this tells you. It also tells you something if you're to the left, right? So what happens to the left, and this guy here will be positive, right? Because then the marginal product of capital will be larger than the depreciation rate. You have an increasing shape. And if you're to the right, this will be smaller, right? Forget about the zero, I don't know what this is doing there. And then you will be on a decreasing. So now this whole story should remind you of something. This is also why I'm calling this here the gold, K-gold. This is what in the solar model we call the golden rule steady state. What is the golden rule steady state in the solar model?
It's the maximum of consumption in each period. Another question, is it realistic to think about economy with excessive capital accumulation, so that there is intervention necessary to reduce the capital stock?
Okay, that's a very broad question. So, so the question, the first question, what do you mean by excessive, right? So basically, excessive here is not going to happen because of our transversality condition. We actually get there, right, at the point. But think about this guy here, like just from the household problem, right? I mean, it will never be optimal to invest in capital forever, right? So that's an outcome of the household problem, right? Because households care about consumption, not about the capital stock. So for them, it could not be optimal to just invest in capital the whole time, right? So this is what you mean by excessive. This is not possible because households will not behave that way, right? We're not imposing this. This is actually an outcome, right? What is realistic in this model that you will have situations where the capital stock could be here, right? You could have situations where the capital stock is higher than the steady state capital stock. You can obviously also have situations where this capital stock is higher than this golden rule. We will actually show you situations. I mean, basically the way how I would think about this is always there's something happening to your economy, right? This is exactly what we will be doing later, right? Maybe preferences change. Maybe suddenly your government changes consumption or whatever, right? And you will see that this always implies changes many dimensions here, and this can then also change the capital stock, right? So maybe what was optimal at some point doesn't have to be optimal again in the next period, right? Because the parameters change, right? Maybe your world changes, right? And this is where it can happen that you're like starting from somewhere which is not these 2 points, right? So this is happening. Does that answer the question? Okay, yeah, but I actually just wanted to get back to this golden rule thing, right? Because kind of, right, something I hope which rings a bell with you, right? Because this is exactly what you do in a solar model, right? In a solar model, you simply go there, there's no household problem in a solar, right? All these maximization, household, utility, Euler, in a solar you just ignore, right? You've never heard of that. But what you do in a solar is exactly this, right? In a solar model, you go and you maximize consumption, right? You basically ask, I'm imposing a steady state, capital, and then you want to maximize consumption. And then it falls out at exactly this condition here, and then you say, okay, if my steady state capital stock is exactly that one, I know we have a maximum level of consumption, right? And this is in my figure exactly this point, right? And this is also kind of why this has to look that way, right? So there is a maximum point where consumption in steady state is maximized, right? So this is this point. Okay. So this is already a lot. Quite questions.
I didn't understand yet how these horizontal arrows come to be. Could you explain that again? Like
These, yeah, sure. Yeah.
Specifically the first one. I don't see how that is like.
Yeah. Maybe let's try to do it from the field. Maybe that's actually easier, right? So the idea is, so this line here, that's what I'm focusing on, right? So this is basically the graphical representation of this condition, right? So where this condition holds, right, with equality. So whenever we are above this line, right? So then you are in a situation where consumption would be higher than this here, right? Right, consumption would be higher, right? You're above this line, right? So here this is consumption on the axis, so it would be higher, right? And this is exactly the situation that you just described, right? Whenever consumption is higher, you're basically eating more compared to what's depreciating of your current capital stock. So there's not enough investment left to replace your capital stock. And this is why the capital stock would decrease, right? So in this situation here, KT falls, right? And this is exactly what these arrows are supposed to represent, right? We're going to the left, right? The capital stock over time would approach zero, right? So this is why this figure basically tells you whenever we are above, we have these arrows to the left, capital falls. And now below is just the counter image, right? So whenever we are below this line, consumption will be smaller, right? So we're eating less than we could, just replacing the capital stock. And this is why capital increases in these two lines, right? The arrows going to the right, and capital goes up. Right? This is actually also, this is on this slide, right? I know these phase diagrams are big, right? So there's a lot of stuff happening. So this is formally summarized here, right? This is exactly the argument that I just gave you, right? So whenever you are in this area that I call 1 here, right? So in my figure, area 1 is that one, right? You're above this line, and you're to the left of the Euler equation. Forget about capital for a second, but let's just take this argument again, right? So then consumption is higher than what you should be, right, to the right. And this is why the capital stock is decreasing, right? And this is this arrow to the left, right? So here you have it formally on the slide.
I find this area 1 a bit irritating because it isn't optimal for the household to then at some point only consume and not accumulate capital.
Exactly.
But that is because consumption right now is a function of capital and not because we're optimizing consumption, right?
Can you repeat the last part? So that is,
our consumption right now is only defined like as a function of capital, so we kind of consume whatever our function allows us depending on our capital.
so yeah, that's very good what you say. So first of all, I'm not saying that we will ever end up in area 1, right? So far I have not said that, right? Actually we will probably not. I will tell you why we do not, right? So far I'm just like describing situations that can happen here. And then we are still looking for the equilibrium, actually. This is not yet the equilibrium, right? So far I'm still describing all these different things that could show up. But it's very right what you say, right? So if you just look at this equation here, this is really just talking about this resource constraint, right? So this is really just how much consumption is there, should there be, to replace the capital stock. If you want to think about household optimal behavior, this is the Euler equation, right? So this is that guy, right? So for that, you really need to think about this equation and how basically that behaves, right? But we'll get to that, right? Where do we actually end up? So far, we haven't really touched that yet. As I said, there's really many things you can do in a phase diagram. This is why I think it's important. But we've only made halfway, so there's still a bit more to come. Okay. Further questions?
So basically, the sector 1, you move left and up.
Yeah.
But how does that make any sense?
It doesn't. It will not. That's exactly. Let me give me a few seconds. I will show you that we will not be going here, but Molly can actually tell you a story why you will not be going there. So basically, maybe I should just continue, right? And then you'll see it, right? So far I was basically describing these two lines, right? So I was also now just describing this golden rule steady state, right? Which is this solo steady state. This would be that one. Right? So now what you would want to ask, right, and I think this is kind of what you already had in mind, right, is what's the equilibrium of this model now, right? What's the steady state, right? So what's the steady state of this model?
It's not K gold, it's K.
Exactly, right? It's this point E here, right? So this point E here, this is the intersection of this line and this line. So this goes a bit in the direction, I hope, of what you were just asking, right? Only in this point do households behave optimally in a steady state, and we're making sure that the resource constraint holds, right? If you're just on this line, households behave optimally, but you could be here, but then the resource constraint wouldn't hold. This could not be an equilibrium, right? If you were here, the resource constraint holds, good, but this would not be in line with optimal household behavior, right? It could also not be an equilibrium, right? So the only steady state equilibrium here is this point E, right? So this is the steady state equilibrium of this model, right? First of all, right? Now the next step will be to talk about how we actually get there. That's the next thing, right?
I just want to know the SB, is that stated preferences, or what does that stand for?
This will be our saddle path, but we get there. This will be exactly this question: how do we get to the steady state? We get there. Right. Okay, so this is the steady state of the model. So now the first thing that I wanted to show you, and this is why I started with the solo golden rule, is exactly as you just said. The steady state K in the neoclassical growth model is not the golden rule steady state of a solo model, right? But it's actually lower. You can see that it's lower, you can see that here, right? So this economy here has a lower capital stock, right? And I mean, this is optimal, right? This is optimal household choice, subject to all these constraints. They choose a lower capital stock compared to what we define in the solo as this golden rule capital, right? Stock. Why is that?
Just a question.
Yeah, sure. Okay.
So, notation-wise, we also would call this K gold in the new classical model, and the other is K gold solo, or is
Yeah,
the golden
typically
rule applied to solo?
we say the golden rule is really the solo thing, and then what you sometimes see is that people call this the modified golden rule, right? They typically wouldn't call this a golden rule anymore, because the difference is, I mean, that's, I'm sorry, you just want to.
It's because of the time preference.
Yeah, it's because of, I mean, you have it on the slide here too, right? So the major difference is, in a solo, you just go and say, I maximize consumption. What do we do in the neoclassical growth model? We write down a household problem. Households don't maximize consumption. What do households maximize? Right, utility. As you just said, utility is this discounted part of all future consumption, right? So here we are maximizing consumption today and in all future periods, we are not discounting. But these households in the neoclassical growth model, they do discount, right? So they live in a world where they care more about today than they do about the future, right? And this hopefully already intuitively explains to you, right? They care more about today than tomorrow because this beta is smaller than 1, this discount factor, right? That the capital stock in a neoclassical growth model will be smaller than in a solo, right? Because households behave differently, and that was basically what I just wanted to answer, right? Also, right, in a solo we call this a rule, right? Because it's basically this ad hoc, we're just imposing this, right? Here, I would not really call this a rule here, because this is derived from optimal household behavior, right? It is microfauna, it is all this stuff that I talked about, right? It falls out of optimal household choices, not just because I'm imposing to maximize consumption, right? So this is kind of also an example of what these differences in terms of why do we microfound, when do we not microfound, what this implies, right? And this is one very prominent example. This is why I wanted to show you this. I mean, you can also formally see this, right? If you look at this equation 16, maybe let me just go back. 16 is that one here, right? If you rewrite this, you can basically solve this for f prime k, right? That's what I'm doing here. Just rewrite this equation. It's really just the same equation, looks a bit different. Then you will see that this thing here will always be larger than delta, And in the solo, you basically get this here as the golden rule condition, right? F prime k will have to equal delta. Right? Here, this thing will always be larger than delta, which is this because of this beta, right? This is very easy to say, right? If this beta were 1, then this thing wouldn't happen, right? Then you would have the same story, but it's not, it's smaller. Right? And this is why they choose a smaller capital stock. Right?
This wouldn't legitimate government intervention, right? So, because it's just because preferences, so there's no place to intervene here.
Yeah, very good. So I mean, in the solo model, right, what you then typically talk about, if you talk about this golden rule, is how do we actually end up at this S level, right? I mean, the golden rule in the solo implies a particular saving rate, right, that we typically call S, right? And then you say, okay, maybe the saving rate, I don't know, in Germany is 20% or whatever. Shall we increase it, right, to get closer to this golden rule capital stock, right? And then you can think about this. Here, this wouldn't work that directly, right? Because it's not just like we can set the saving rate, right? In a solo, you basically live in that world, right? Policy can maybe affect the saving rate. The saving rate in the neoclassical growth model is endogenous, right? So it's a result of how households behave. Still, you can try to adjust it, right? We get there, I'll show you some applications, right? I mean, you can add government spending, I'll do that. You can also add other stuff here. You could think about, for example, once you have taxes that change over time, people would also adjust their saving, whatever. You can do stuff, but it would work very differently compared to the solo. Yeah. So feel free to. Okay, good. So yeah, again, we will talk about the dynamics in a second, right? But that's so far the steady state of the model, right? And what we do with these 4 areas, we get there in a second, right? Because that's exactly what I want to do next. I suggest that we have a short break first. Okay? Good. Und dann machen wir 5, 4, 3, 2, 1 und lassen die Arme locker fallen. Nehmen wir die Ellbogen auf die Hüfte, die bleiben fest am Körper, Handflächen nach oben und dann drehen wir mal nach außen, soweit es geht, ohne dass die Ellbogen sich lösen. Ja? So weit drehen, wieder vor. Wir drehen und wieder vor. Die Ellbogen sind fest am Rücken, nur das Ziel. Und dann machen wir noch 5, 4, 3, 2, 1 und locker lassen. Jetzt müssen wir uns ein bisschen bewegen. Schaut mal, ob ihr Platz habt. Es geht wie folgt. Zeigt einmal, wir wollen mit den Ellbogen vor dem Körper einmal an das Knie drücken. Wenn das nicht geht, lasst es die weg. Ihr geht nur vor und ich will wieder auf. Also die Wirbelsäule nach vorne und schräg bewegen. Darum geht es. 1, 2, 1 und einmal wechseln. Wenn es nicht geht, und wenn es zu eng ist bei euch, dann machen wir nur die Rotation wieder auf. Nein. Das war richtig, ja. Zu viel in der Hosentasche. Und wieder hinstellen. Dann machen wir den ersten Arm, der kommt wieder in den Kopf. Dann machen wir weiter. Und zwar jetzt seitlich. Entweder mit Knie oder ohne. Neben dem Körper ans Knie drücken oder einfach zur Seite rein. Geht auch. Ja? Ich möchte das Platz haben, das Knie mit. Wir drehen die Wirbelsäule seitlich. Und noch 3, 2, 1. Ja. Seite wechseln. Okay. Mal schön vorsichtig mit den Nachbarn. So schnell die Knie abbekommen. Sehr gut. Oder ohne Knie. Noch 3, 2, 1 und locker lassen. Sehr schön. Dann einmal die
Dafür komme ich zu entweder langer Arm oder wenn die Nachbarn eng stehen, können wir den Arm auch anwinkeln. Ja, wir ziehen den Arm an den Körper, sodass wir die Dehnung an der ganzen Schulter aussetzen. Und auf der anderen Seite langer Arm oder angewinkelter Arm, so wie es geht. Das Gegengewicht ist Klo. Und lassen locker. Und dann kommt die letzte Übung für heute. Wir nehmen die Hände einmal mal in den Kopf. Und dann die Wirbelsäule einmal nach vorne reinrunden. Und ganz bewusst strecken, Ellbogen zurück, Brust raus, richtig bis nach hinten legen. Einmal durchstrecken. Und nochmal Wirbel für Wirbel eingerundet. Wirbel für Wirbel durchstrecken. Und nochmal. Und beim letzten Mal atmen wir einmal kräftig ein, aus. Und sind bereit für die nächste Zeit der Vorlesung. Danke fürs Mitmachen.
Ja, dann merkst du
So now let me move towards your questions about this, why we need these 4 areas and what is this SP, right? Because that's exactly what I haven't touched so far. That's where we're going to go now, right? So let me try to start this with you thinking about this a bit, right? So I mean, roughly speaking, what I just did, right, I defined the steady state, right? I showed you the steady state is here, right? Point E. I mean, you can also see where the steady state is not here, for example, right? You remember also our solar, right? Where we were kind of having similar discussions, right? It's this well-defined point E. But what actually makes sure that we will ever be in point E, right? That also goes a bit to your direction, right? Here in this economy, nothing forces us to be in point E, like from the start, right? Will we ever be there? How will we end up there, right? So that's questions we have to answer here, right? Because I mean, this is also related, this is a dynamic model, right? So you should think about how these values all behave over time, right? So this is exactly the situation that I create now here on this slide. I hope you can see this, right? So this is the same figure. The only thing that I change now is now to say, think about this capital stock K0, right? This is supposed to be our economy where we start now, right? So like we wake up, this is the economy that we live in, and this is the capital stock that we have inherited, right? K0. And as you can see, it's smaller than the steady state capital stock, right? So this economy here is not in a steady state, right? And this is a situation that can happen, right? I mean, actually I would say why would we ever be in a steady state, right? Why should we? Here we are clearly not, right? So we are out of steady state. And I mean, just to make that clear, right? Out of steady state does not mean out of equilibrium, right? This will also be in equilibrium. This is 2 different things, right? Okay, so this is K0, this is where we are, right? So now my question is, right, that was basically the first point here, right? What is now going to happen with K and C, right? So with capital and consumption in this economy over time, if households, right, basically in this situation K0, households wake up and they have to make a decision now about how much to consume. What will they consume? What will C be, right? I mean, and that's really the idea of the model, right? Households make their choices, right? It's a household optimal consumption choice. What do? Say they consume CA, right? So they consume this here, so you would basically be starting in this point. What would happen then to K and C, to consumption and capital over time, if this is the initial situation? So this is my question. What K fall, C rise, would K first fall, then rise, C rise, K rise, C first rise, then fall, or K first rise, then fall, and C rise, right? I mean, this is all, we'll just think about the figure, right? So what would happen with K and C starting from this point here that I just marked? What do you think? Take a second and think about it. I give you one more minute. Yeah?
I guess that K will increase as we are consuming less than we could consume.
Mm-hmm. Okay, will increase. Who's agreeing? So how can you see this in the figure? This is kind of right. This
Basically, for every point under the accounting kind of equation, KO is increasing.
exactly right, and yeah.
And I think because we didn't cover this SP part yet, but that's what determines C, because the utility.
But that's the next slide already. Yeah, but you're right. Yeah, exactly.
I mean, every point that is to the left or above this dotted line is like too much consumption than the consumer.
Let's see that we get there. Basically, you're going in the right direction. But that's actually already the next part. So far, we want to think about this point, which is not yet on this dotted line, right? But it's exactly right what you said, right here. Capital is going to increase, and in the figure you can actually see this, right? Because this red point that I made here is in this area 3, right? And this area 3 is basically described with these two arrows, right? So this one here tells you capital goes up. It also tells you something about consumption. What does it tell you about consumption? It also goes up, right? And the story of capital is exactly what you just gave, right? We're below this resource constraint, right? Why does consumption increase? Well, because the capital stock is lower than the steady state capital stock. The marginal product of capital is pretty high. This is why people will save more, right? And they will consume more in the future, right? That was the story from the oil equation. Right? So this is what describes this area 3, right? In area 3, we're basically moving up right here, if you want so, right? But what happens here if you're moving up right? So you see, I've just plotted it, right? I'm now hitting this black line. So what's happening now?
On the line, the capital stock stops growing.
Mm-hmm.
It's against our preferences, so our consumption and our capital stock will increase up to the maximum of the graph, but it's against our preferences.
Yeah, exactly. Right, and that brings me to your point. But first of all, it's exactly right what you said. We're hitting the black line, right? And I mean, on the black line, this is a steady state from the perspective of the resource constraint, right? But it's not a steady state from the perspective of the oil equation, so that's kind of what you said, right? It's not aligned with optimal household behavior. Households will still continue to save more, right? So they will still invest more capital. And this is why at some point you see that consumption keeps increasing and increasing, right? But at the same time, here we're now over the resource constraint. This is why the capital stock now starts falling, right? So we're basically, like from the figure, we're entering here now this area 1, right? We were starting in area 3, but once we hit this line and we cross this line, we're entering this area 1, and then consumption keeps growing, but the capital stock suddenly starts decreasing, right? Because we crossed this resource constraint, right? Suddenly we're like eating more than we should, right? That was this image I gave you, right? And then happens exactly what you just said, right? We're moving to the upper left part of this figure, right? And this upper left part of the figure, this is kind of where you were already heading. Is this an equilibrium? Doesn't look like one, right? We're moving somewhere, but very far away from the steady state. Going up there can never be optimal, right?
So basically, intuition-wise, we increase our consumption and then we go back because our capital gets lowered, and so we return to the steady state. And that's why the steady state is small.
Well, here we're not returning to the steady state, right? I mean, the steady state is this point east, right? The steady state would be here,
Yes.
right? So basically, the point the point I want to make is that with this consumption choice CA, you will never end up in the steady state. You would actually end up somewhere, and this is kind of what you were already alluding to, is households will not choose CA. They will not do it, right? Because it's against their preferences, right? Here we're going in a situation where consumption would be super high, capital would become low. This is actually what we typically call, maybe you've heard it, like a Ponzi game. And we're basically saying these models, we're excluding that by construction, right? You will get to a situation where people like keep accumulating that. And this is just not. Right. Okay, so people would not choose CA, right? The reason why I wanted to show you this is to like get this, why this figure helps you to understand this, right? And what these different areas do. So now let's think about, so what does that mean? So what's the right answer now? So K first rises, then falls. C rises, right? It's D, right? So basically the correct answer to CA would be D, right? So now think about households choosing this point CB. What would happen then? Where would the economy go?
First, both would rise again. But then I assume at some point we hit the vertical line,
Exactly.
and then we drift downwards with respect to consumption.
I'm not sure my drawing is the best, but you see what I mean, right? Exactly, right? First we also go up, right? Just as we did here. And then we're hitting, at some point, we're hitting the Euler equation, right? And once we hit the Euler equation, we get in a situation where the capital stock keeps growing, but consumption is not decreasing, right? This is now area 4. This is now these arrows that matter, right? And what's happening here? Here you're approaching a situation where the capital stock would become very, very high, but consumption actually approaches 0, which is, I mean, already intuitively never optimal, right? How could this be optimal to go in a situation where where consumption is equal to 0? Here you can actually make the argument in a very simple way and say, okay, consider a household, the household would instead have chosen this point. The household would have been better off in every situation compared to this point CA, right? Because consumption would be higher. So this is why it could never be optimal from the perspective of the household to choose CB. They will just not do this, right? That's not optimal household behavior, right? The formal way to say it, it's not in line with our first order conditions, in particular here with the transversality condition, right? Because this is basically the transversality condition biting here, right? This here would approach 0, and this is exactly what your transversality condition prohibits, yeah? Okay. Which means the correct answer here would be C, right? K rises, C first rises, then falls. Yeah, exactly, right? So just to make sure, right, what I just said is all on this slide, right? Why is CA not, I mean, here I'm already using the word cell pass, sorry for that, right? But starting from CA, this is exactly what's happening. When we go towards this with 0 savings, very high consumption, this is just not what we want the model to do, right? CB is also not optimal, right? This is exactly the optimum that I just gave you, right? It's here on the slide. So your households will not choose CA and they will not choose CB. That's against their optimality conditions, right? They are not doing this. But what they do, and that is your question from earlier, right? They will choose exactly one point, which is graphically here the point of this dotted line that we call the saddle path. But this is the reason why we call it the saddle path, right? So on my earlier slide I call this SP, right? The saddle path. So what households will choose is this point here, because this is the point that brings me nicely here to a steady state in point E, right? Right? See that this is, I mean, we're doing the same, it's the same direction at first, right? Consumption increasing, capital increases. But this is the only trajectory, if you want so, right? That brings you to exactly to the steady state. Right? And this is the only choice of households which is consistent with optimal behavior. Right? So this is what they will do. Right? So this saddle path tells you something about what happens if you're off steady state and how do households then choose their behavior. And then you can see that's only this, that this is the reason why we end up in a steady state. And this is basically where we are on this line. And this is very different from solar, right? Because in solar we don't have households doing anything. They just have to do whatever you tell them to do. Right? Yeah, there was a question.
So we were asking ourselves why there are different slopes of these curves, because they are both starting at K0. So the marginal product of capital should be the same, and therefore shouldn't have both of them have the same slope, or not even like the
So what curves are you thinking about? The resource constraint and the saddle path?
the length that you
Or those that I've been drawing here?
yeah, why do they have different slopes? And shouldn't the slope of the lower one be even higher because we have less consumption and therefore we increase capital by all of that what we're saving as well, in addition to what we invest?
Yeah, I mean, like what happens across these slopes, right? I mean, you have to take into account not only the resource constraint, I mean, the resource constraints of the marginal product of capital and so on, right? But these are also driven by optimal household behavior, right? So along these lines, you would have to think about households make assumptions, I mean, they know everything, right? So households think about their future consumption choices, right? So think about this Euler equation. So basically, these lines here will be in line with your future consumption path, future returns on consumption. So this is all part of these equations, right? And I mean, the future consumption here is clearly different for that line and that line, for example, right? And also for that line. I mean, here future consumption at some point is constant because you're in a steady state. Here future consumption keeps increasing and increasing, and here future consumption actually goes towards zero, right? Like, just think about the other equation where future consumption shows up. This implies that I will be behaving differently across these different paths.
You know,
Right.
why are there different paths?
Because you're starting in different points, right? I mean, basically, the way how I want you to think about this here is, I mean, again, right, these points CA and CB, they will not happen, right? And I'm kind of trying to show you why they will not happen, right? But let's say, for some reason, households choose that point, and then from that point onward, they behave accordingly, right? This is what would happen. And this is kind of what explains that in the end why this is not happening from the start. Right? But also, I was just drawing these lines, right? So you don't take, I mean, you need the slopes here to be different, right? Otherwise you would end up here, but it's also an illustration, right? So
private Fleming and
Exactly. So that's maybe that's a very good way. Let me try to explain it that way once more. Yeah, maybe let me even, sorry for jumping, but maybe let me go back there once, because maybe that explains that. Right, that's not working. So when we defined the equilibrium, right? So what I said here is, what you need, you have an initial K0, right? This is exactly how I started in this figure, right? We have an initial K0, and then you basically have all these first order conditions and everything. What you need then is the starting value for consumption, right? And this is basically what I mean with the CA and CB, right? I'm kind of taking arbitrary starting values for consumption now. And then I'm basically solving the model through and show you that with these two starting values, it's not working, right? So that there's only one starting value for which we are moving nicely towards the steady state, and this is the one that households will choose, right? And this is kind of the graphical proof that this economy here nicely moves towards the steady state. But that's why I want to get this across. We're not imposing this here, right? So we are starting off steady state, and then we can actually think about the transition towards the steady state. Right? Okay. Sorry, this is too slow. Yeah, this was my figure. I'm not sure it was nice, but exactly. Yeah, I mean, basically you have it on this slide here again too, right? So we have this initial value of K0. I think I said before at some point, this is why we call this a state variable. This is what we're conditioning on, right? Households wake up in the morning, this is what they see. And then households have to think about what do we do now? How much do we consume, right? And this is this consumption choice. This is this C0, right? And what I basically wanted to show you here is that there's only one choice of C, only one consumption level, which is consistent with all these equilibrium constraints that we have defined. Right? And this is basically, I mean, this is going to happen not only for K0, right? But you could make the same argument for any other K here, right? You could make the same argument here. Say I'm starting here, right, in a K1, whatever, right? You could also do the same thing. And again, you would be adding up on this one particular point on this what we call saddle path, right? And then again, you would be moving towards the steady state.
Does steady state change under which circumstance?
Yeah, we'll do that. Give me some time. I'll show you how it's going to stay.
But you already did that, right? Because the slope was changed. Because that underlying this kind of slope was changed. You already did that?
When did we do this?
I mean that while you explain the two correct answers, and you already changed the slope, right?
Yeah, very good. So I mean, the steady state so far is always the same, right? I mean, this point E here I haven't touched, right? So that guy is always the same here, right? So like this black lines here, not change them at all, right? So basically the only thing that I'm doing here, I'm kind of like showing you what happens if you start at a point which is not on the saddle path, right? Now I can use these words, right? I have defined it, right? And this is basically, think of this here as an, and that goes also back to your question, right? Think of this here as an imaginary way of how consumption would evolve and the capital stock would evolve if this were the initial situation, right? This is also where, as you said, the slope is different, right? Because this is a situation where we will not be ending up, right? Does that explain that?
Not
so
very.
I'm not changing, by doing this exercise, I'm not changing this black lines here, right? And I'm not changing the steady state. So I've not changed any of these equations, right? This is all staying as it was before.
But how can you have the two answers for the correctness?
Well, because sorry, that's probably my Aki notation, right? So basically, D this refers from, if you start from point CA, right? And C refers if you start from point CB. Right? If you start from point CA, which was this guy here, right? CA is here, you get these dynamics, which is described by what I have verbally here in D, right? And if I start from CB, I get these dynamics, which is verbally described here in C. Right? All right. Good. I think we discussed all of that. So why does this all matter now? Why do I need this? This also goes a bit in the direction that you were asking earlier, right? Why would I ever have a situation where the capital stock is below the steady state, right? I mean, this is always how I started here, right? I mean, note you can also start in a situation if the capital stock is too high compared to steady state, right? You would be moving from above that, right? So this would be working too, right? So why would this ever happen? Is that a thing? I mean, to be honest, I would say most economies are out of steady state, I would guess, right? So I think this is a thing, right? Why would we ever be in steady state, right? And this then here tells you something how households optimally respond to this, right? So basically, just intuitively, what happens in these models, if you're to the left, right? If your capital stock is lower than steady state, this marginal product of capital is high, right? That was our argument from the perspective of the other questions, right? So which means that the return on investing will be relatively high, right? So households will do this, right? So the return on investment, think of this as the interest rate, right? So the price for saving will go up, right? And households will respond to this, right? And this is exactly what makes saving endogenous here, right? The price for saving goes up, the interest rate goes up, and this means that they will save more and you will see more investment in this economy, right? And this is not happening in a solo. What happens in a solo? You can just go back to our chapter 2, right? And so you just have this exogenous rule, right? So we're saying we are saving X% of output, whatever it is, right? I don't care about interest rates, about prices, right? Households will always choose to save 20%, right? Here this is different, right? And this is the major change, right? So we actually make saving endogenous, right? Yeah, and I mean intuitively what this is doing, right? Say the capital stock is lower compared to the steady state, you have a higher return on saving, they will save more. They will basically cut back on consumption a bit today, by that consume more tomorrow, and rebuild the capital stock, right? Right. Okay. Good. Yeah. And I mean, just to say that, I mean, I said I sometimes find those papers, maybe you find it interesting, or I don't know. It's just, I mean, these phase diagrams, right? As I said, I'm showing you the phase diagram in the context of neoclassical growth model. Obviously, you can use the phase diagram to any dynamic model, right? It doesn't have to be a neoclassical growth model, right? So this is one very useful tool. This is also why I'm showing you that, right? In the neoclassical growth model, it's all about capital, right? So this paper here is actually about it. I'm just pointing, you don't have to read it, but maybe you want to open it once. You will actually find phase diagrams in that figure too, in that paper too. But it's about the optimal destruction of vampires, so it's actually like a very different setting, right? So just to point that out, right? If you're fed up with capital and labor and whatever, this is just a very different application. And to me, like always a nice example when you can use these things also in different contexts. So you can use it in any dynamic model, right? Good. Okay, so then let me some more model applications, because I also hope that this makes it a bit clearer, right, what you can now actually do with this model, because this is then kind of what, I mean, is to me always what I want to understand from the model, right? I would say we have now, in a way, solved the model. We have not like written it down in terms of quantities, but we have this graphical tool, which is the phase diagram, that we can use to think about what's going on in this model, right? So let me give you an example, right? So let's say here, right, as I said, right, this was my example, households wake up, they inherit a capital stock, so now there's something else happening here, these households now wake up, and they discover that their preferences have changed, right? So they now discount utility at a lower rate than they did before, so they have a higher discount factor, which basically means, right, in words, I suddenly care more about the future, right? Tomorrow now matters more than it did yesterday, right? And I mean, maybe that's also one thing you were asking earlier, like, can we think about policy here? I mean, this is not policy, right, because I'm changing preferences. I mean, maybe policy was responsible for that, even though I wouldn't really know how they would do this, but so we can change stuff in this model and then think about what it's doing, right? And this is exactly what I want to do now, right? So what I do here is, like, in terms of the model, very simple, right? I just say we increase this beta factor, right? So maybe before it was 0.95, and now you increase that to 0.99, right? So suddenly we care a lot about the future, right? So what's happening, right? So the discount factor does not show up in the resource constraint. The discount factor only plays a role for households' consumption saving choice, so it only shows up in the Euler equation, right? So it's here, right? So it's going to affect the Euler equation, and I mean the easiest way to think about this, and I mean that's what we have the phase diagram for, is to think about how it's going to affect the phase diagram, right? So think about the steady state. So what this here shows you, this was the steady state equation from the Euler equation. So if you increase beta, right, so that guy goes up, you will need a higher capital for consumption to stay constant, right? So I mean, maybe just to show you that from the equation, right? This has to equal 1, right? So you have an equal here, right? So if that guy goes up, something here in the right-hand side of this parenthesis here has to decrease, right? Otherwise this thing wouldn't equal 1 anymore, right? Delta is an exogenous parameter, is a depreciation rate, right? Whatever households do, they will not change delta, right? So this thing is constant. What households can do is they can adjust their consumption saving behavior, their consumption choice in particular, right? Which then is going to affect steady state K, right? Which is our endogenous variable here, right? So K is going to change. How does it have to change here to make sure that this thing here gets smaller? Well, I mean, if you have a higher K, right? If K goes up, F prime K falls, right? That's the story about the marginal product, right? The more capital you have, the lower is the reach kernel capital, right? So that means a higher K implies that this guy here falls, and then you can have a situation that this still equals 1, right? So that your equation still holds, right? And a higher K in my phase diagram means that this curve here is shifting to the right. Right? So now you're back in macro, right? I'm shifting curves. That's what we do, right? So now I can do this again, right? So this is basically this here is my old Euler equation, right? That's the way to read it. This here is the new one. So by increasing beta, we are shifting these here to the right. Right? Otherwise, this is the same diagram, right? And now I can tell many stories, right? But this is what you have this thing for, right? So maybe let's focus on the old steady state first, right? So this here, this point here, call this A, so I can call this A or whatever. Let's just start with this point, which this is the old steady state, right? So So this was where the economy was before, everything was in steady state, consumption was constant, capital was constant, all good, right? C old, K old. Note that this is both not indexed within T because this is steady state, right? Now these households wake up, their preferences have changed, so we suddenly have a new Euler equation, which is here, which means that the new steady state will be here, right? I mean, that's easy. That's basically like an ISLM what I'm doing, right? So the new steady state will be here, where you have higher consumption, higher capital stock in the new steady state. Right? That's maybe not too surprising, right? Why do we have higher capital stock? That was just from the slide before, right? People are more patient now. They just save more. They care more about the future. You have a higher capital stock, and that also allows them here, because we were starting on the left-hand side of the golden rule, right, to have higher consumption in the future, right? This is just what you get. What is interesting now, what is new, what you can learn from this phase diagram is how we get there. Because this K old, right, the capital stock is, as I said, right, it's a state bubble. We cannot change the capital stock in that period when we wake up, right? In the period when we wake up and discover our preferences have changed, the capital stock is there, right? I have to work with the capital stock as it is. And you can basically see what that makes households do here. And this is now the cell part that is relevant, right? So what they will do, they will go to this point A, right? This is why I have marked that here. And what this point A implies is that they will, to a large degree, decrease their level of consumption. Right? Because in this point K, old, they're basically waking up, they have these new preferences, and they see, well, guys, look at this, the capital stock was way too low, right? We actually care a lot about the future now, we should save more, right? And they do this immediately by reducing their consumption a lot, right? But they cannot change the capital stock in the initial period because this is just given. Right? But what this then does over time, this is basically these little arrows that I have from the cell part, right? And now we can think about these four areas that we define in this phase diagram, right? It will allow them to not suddenly, but like step by step, over time, increase consumption and increase the capital stock back to, or actually not back, to the new steady state. Right? And this is what the models, or what these dynamics are about. So, and I mean, another way to look at this, and I mean, before I said we have no T on the axis, but maybe let's think about having T on the axis, right? So what does this imply if you plot consumption, right, with the T on the axis? Let's say this here is what I call C, no, this here is, sorry. This here would be my period 0, right, where households suddenly wake up. So what happens with consumption in that period? What was this here? Consumption falls, right? It falls a lot. So in this figure, it would tell you, okay, this actually, right, I don't know, let me define this here as 0. So consumption would really go down, right? People consume less. But then over time, what this figure tells you, consumption is going to increase again. And it actually increases by more compared to where we came from, because the new steady state is higher, right? So you could plot something like this here, right? And at some point we're converging to the new steady state. So this here would be C U, right? So this would be the dynamics of the consumption here, right? So you basically really see how households cut back on their consumption to build up the capital stock. And then over time, because the capital stock is building up, they can actually increase their consumption, right? So you can also plot the capital stock if you want. How would the capital stock look like? With the T on the axis. Say this is 0 again.
You would just
it would slowly increase, right? That's the important thing, right? I cannot just increase it from period 0 onwards, right? The capital is this slowly evolving thing, right? Basically, you have to invest and invest and invest, and then over time, I'm increasing my capital stock, right? And with capital, I mean, you could also put output here, right? Output, which is look exactly the same. You would also be increasing the output of the economy. And I mean, this is a bit, maybe you've heard of the impulse. So yeah, go ahead first.
And why do we start at a consumption level of 0? I mean, you cannot consume more.
Yeah, very good, because I was actually confused by what I was just about to say. We should actually, this year is actually CO. Yeah, thank you. This is where we start. Yeah, very good. Have you ever seen impulse responses? This is just where I was about to go. So whenever you go to a talk in macro, at some point you will see impulse response, and they look exactly like this, right? With what we call IRS, this is exactly what we ask for, right? Impulse response will always give you, there's something happening in the initial period. Here what's happening is this change in preferences, right? And then we ask over time, how does my economy adjust? So what's the response to this impulse, right? Over time. And this is basically already a way to represent that, right? Later, I will show you this here again, right? So we will also do this. And you can, at some point, right, once we open the computers, you can compute every single point on this line, right? It's not just you have to always just draw it. For now, I'm doing this, but later you can actually compute it. Right. Good. Yeah, maybe there's two more things to point out, right? So this is why the saddle path is important, right? Because the saddle path tells you for whenever you are off steady state, right? And you can make up many situations that will be out of steady state, right? And then it tells you something about how your economy is moving over time. So I mean, this is one of these things where also in the solar, right? This is actually like the argument is similar again, right? Say an economy which is very far off from the optimal steady state would be growing more, right? This is exactly what's happening here. Right? So this is this first thing. This is why the saddle path is important. And the second thing is what we see here, right? You can see that consumption really is adjusted immediately. Right, so consumption is the thing that is adjusted from one period to the next. This is what we call jump variables, right? It can jump to the new level immediately. This is kind of what I wanted to point out this year, right? This is a jump, right? Whereas capital cannot, right? Capital is this slowly evolving thing, and kind of this is also very important to have these two things. Okay.
Can you explain what is jumbo? How to say that? Jungle variable.
Jumbo, yeah. So yeah, I mean, so the jump variable here is consumption, right? So like the overall definition of a jump variable is it's the variable that can adjust immediately to any shock, right? So the shock here would be the change in beta, the change in the discount factor. And there's one variable in the model that's adjusting immediately, that's the consumption. That's the jump variable. Whereas the other variable, which is capital here, cannot. Okay. And basically in the figure you can see that here, right? So consumption really drops, or you can actually see it here, right? Maybe that's easier. Consumption drops immediately already in this period 0. Whereas the capital stock is, we say, predetermined. In period 0, you're not able to adjust it immediately, it's just there, right? You first have to invest, and that takes some time until we're actually building up capital. Okay, good. So I mean, just to make a big picture, right? I mean, I'm not saying that it's overly realistic that we all wake up in the morning and our preferences are changing, right? The thing that I want you to show here is that we can do such experiments in this model now, right? And I mean, as I said, this is to me what we have these models for, right? So we want to then change parameters and see what's happening, right? And what I want to show you next is that we can actually introduce government spending in this model and think about what a change in government spending is then doing, right? And this then weighs that a bit, I hope, right, towards policy application, right? Because you can actually, I mean, the model is super small, right? But you can think about this here already, right? And this is basically using exactly these techniques of a phase diagram to analyze this, right? So that's where I want to go, right? So the phase diagram, in that sense, is a tool for doing these experiments with our models, right? And that's what I want to show you, right? And the next experiment that I want to do is exactly this, right? Let's think about fiscal policy in a neoclassical growth model, which is actually an interesting exercise. That's why I like. That's why I like doing it. Okay. Good. All right. So then let's close this here for today, and then I'll see you next week. Okay.